So, thank you very much, Yaron. So it is now my great pleasure to invite Professor Artur Ekert, who is a distinguished professor in the National University of Singapore. And he will talk about Bell inequalities, from curiosity to security. So, please.
Thank you very much. It's a great pleasure to be here and to see many familiar faces and some of my colleagues and friends. I'm going to give a very basic presentation. You know, when you ask to give this kind of talk and you have your congregation is somewhat mixed, right? So some of you have background in computer science or maybe security or maybe crypto, some of them in quantum physics. So sometimes it's very difficult to find a common denominator, but you know, there will be some equations though, but you can just gloss over them and there's the main concept or the main narrative of my talk is essentially to show that quite often when you do basic research and you start in the area that has, you know, a priori nothing to do with something else like practical applications, sooner or later it turns out that it is in fact relevant for all those practical applications. So as a spoiler for this talk, I'm going to show you two narratives. One is curiosity-driven research, trying to understand the meaning of quantum physics. And I'm not going to go into all nitty-gritty details. Actually, I'm going to follow one particular line that will take us to John Bell and Bell theorem. And on the other side, equally fascinating history of trying to design a system that by two people can communicate with perfect security. And so then I'm going to show how those two different quests, you know, one curiosity-driven research where the objective was trying to understand the notion of randomness, certain aspects of weird correlations that may appear in nature. On the other hand, trying to design a system where people can communicate with perfect security and also trying to understand randomness and the nature of randomness, which was equally relevant for secure communication. And at some point, those two narratives will merge and give them sort of rise to what we believe today is the most advanced form of secure communication. Now, to those of you who actually are, you know, hands-on on crypto and cybersecurity, you may find it very academic, and it is. I'm not going to go, even though there are some interesting implementations, applications, but it's fair to say that for hardcore, my colleagues who really work on cybersecurity quite often find my stories amusing more than practical. So they are in this kind of layer, so don't apply this criterion to them. But eventually, you know, as it happened many times in history, those wacky and crazy ideas find a way to practicalities. Okay, so let me start with the first narrative, which is the quest to design a perfect cipher. And you know, the history of cryptology is a fascinating topic, and one can give a number of lectures about this. But essentially, this sort of the art of secure or you know, cryptology, the art of hiding messages or writing them in a way that is only accessible to certain people is as old as writing itself. It goes to ancient Egyptians, then Greeks and the Romans. And then you probably all know stories about Enigma machine that was broken by the Polish cryptologists and later on also by Bletchley team in the UK. And then the new and interesting mathematical development of public key crypto systems. And eventually, you know, if you ask the question, was it ever the case that we design a perfect system, a system that is unbreakable, that we can be sure that nobody can break this system? The answer is actually kind of yes. And the kind of yes points into something that is called a one-time path. And the idea of this cipher is very, very simple. So you have two individuals that we always call Alice and Bob, of course. And if the two of them share a binary string of a certain length, a random selection, truly random selection of zeros and ones, which is secret, known only to Alice and Bob, and you can see it on my diagram here. This is this yellow part, sorry, the red part. So you then, as one user, Alice, can take a message, write it in a binary alphabet of any choice. At this point, it could be like ASCII code. And then what Alice can do, she can take every single bit of her message and add to the bit from this cryptographic key. And the addition is a binary addition, so it's just like any addition except 1 + 1 is equal to 0. And when you do this bit-by-bit addition of the message and the key, you get a cryptogram. And the good thing is that if the key is truly random, then the cryptogram inherits this randomness, so that the randomness of the key is transferred to the randomness of the cryptogram. And any statistical analysis of the frequency of characters, any sort of tools that people develop, statistical tools to handle or to break ciphers will not work in this case because it's a truly random sequence of zeros and ones. So then Alice can send this cryptogram over an open channel to Bob. Now, assuming that Bob has the key, the same sort of sequence, the red sequence of zeros and ones on my slide here, then Bob can simply perform the same addition and recover the message. So he's going to take something that looks random, add this random key, subtract this randomness, and get the message. So Claude Shannon, who was the founding father of cryptography, modern cryptography, showed that under certain assumptions, and those are that the key is as long as the message, the key is never reused, the key is truly random, whatever random means in this case, but each bit is selected with probability, say 50%. So, so under those assumptions, the system is unbreakable. There is, however, a big problem there, right, as you can guess. The fact that we should not be reusing the key. So it's called one-time path. Once you use the key is obsolete. You just drop it and try a new key. So the problem is the key distribution problem and how the two users who are miles apart should generate those keys. And this requires a very secure channel. It could be a trusted courier. It could be a very secure telephone line, whatever. But it's something that is usually difficult to set up and equally difficult to certify that it is absolutely secure. And but once you can estimate, so if you have such a secure channel, and once you can estimate how much noise you have and attribute this noise to potential eavesdropping on the channel, you can, the computer scientists develop a series of interesting techniques where you can take something that looks like a partially secure transmission and reduce it to a pretty secure string. So usually you just take a binary string that is of a certain length and you say, well, the noise in the channel tells me that maybe an eavesdropper knows some bits here. And therefore, let me just do something called privacy amplification or randomness extractor. And this process will allow you to contract the string into a smaller one, but the smaller one will be actually secure. So those techniques are known, and people develop them in crypto. But the problem here is to estimate, in order for those techniques to work, there's this very important initial condition. So you have to be able to put an upper bound on how much information leaked to a potential eavesdropper. So, and this is basically impossible because, at least in a classical domain, no matter how you do it, the characteristic of the channel usually doesn't give you this possibility to put an upper bound on the amount of information that leaks to a potential eavesdropper. And this is the problem, right? So I'm going to come back to this problem and show you that at the very fundamental level, quantum physics allows you to put an upper bound on this value. So you can, by inspecting your channel, you can actually say how much information was leaked out there to any external entity. But for now, let me just switch to another narrative, and that will be actually a dominant one, the curiosity-driven part. So that is the part where people were essentially looking at the foundations of quantum physics and asking themselves questions about the nature of randomness that somehow popped up in a very different way than the randomness in classical physics. And so the story, perhaps, it's fair to say that as everything in the history of Western science, you just basically look at the ancient Greeks and they had some ideas about things. So when you investigate the history of randomness, which again is a very interesting topic, there are essentially two schools of thinking about randomness. So one school is to think about randomness as the lack of knowledge about something. So you say, well, this thing may be not random. Someone who has better knowledge, better insight would actually know what it is. But because you don't know, so things may appear as random. So this is like a subjective perception of randomness. And if you look at the ancient texts, and then probably Democritus about 400 BC was the first one to advocate this view, saying, well, atoms, as he understood, follows predetermined path, and there's not inherent randomness in nature. In contrast, for example, Epicurus, who came a bit later, was convinced that there is inherent randomness in nature, that somehow atoms swerve, as he called it, when they just follow a certain path. So there are those two schools. Is it objective or is it subjective? Is it really there, whatever that means, or is it just simply lack of our knowledge and the whole nature, the whole universe is essentially deterministic? It just we simply perceive it in a way that it looks random to us. And of course, there's Aristotle who had a view just about on everything. And so he basically had this argument saying that science by its own nature is causal, right? And chance is this break of causality, and therefore it's not part of scientific investigation. So he kind of dodged the question, I guess. The first, for various reasons, the studies of randomness from sort of more scientific point of view came quite late, and they're associated with gambling. And not so much with the French, because usually the typical story goes, it was the Frenchies that came up with the first description and first understanding in the context of gambling. But a century earlier, there was an Italian chap, Girolamo Cardano, who was the first one to quantify the concept of probability. So he wrote, he was actually quite one of this, back in the early 16th century, you can actually be a polymath. You could just say a sensible thing about everything that humans knew about at the time. So he's more famous as someone who found the solution to the cubic and quadratic equations in his very influential book called Ars Magna. And also in this very book and some other books, he introduced complex numbers, or at least square root of -15 that appeared. And he called these numbers completely useless. On the other hand, he was a gambler, a notorious gambler, and he wrote a manual for gambling where he introduced the concept of probability. So quite often, when I give lectures in quantum physics, I like to start with Cardano because he himself discovered two basic tools that we use in quantum physics: complex numbers for amplitudes and probability to describe the outcomes of the measurement. So in a way, it's a kind of interesting coincidence that the two basic tools, complex numbers and probability, lead to the same person in the early 16th century. But of course, later, So Cardano defined kind of the concept of probability and played with this a little bit. He was interested in the notion of fair game. But then, you know, how to understand the probability, another lecture and another, you know, views that people had. But again, essentially, it was just the question, what it really means. What is it? Does it reflect lack of knowledge? Can you understand it in terms of frequencies, like von Mises wanted to see it? Maybe as a sort of a betting strategy, a very subjective thing, like Bruno De Finetti's approach, maybe like propensities, that was Popper's approach. You know, a number of different people thought in different ways. But the mathematicians came quite late to this game. And the reason for that was that the notion of probability as formulated by Laplace and others was, the definition was circular. The definition was essentially take the number of cases in which event A appears and divide by the total number of cases. But this definition only makes sense when those events are equally likely, right? So they have to be equally likely, and then the concept of that you have to measure probability to find equally probable cases and count them is circular, because by saying equally likely, you already invoke the concept of probability. So that changed drastically when a Russian mathematician called Mogorov said, you know, in a very mathematical way, he said, you know, I couldn't care less what this really means. I define a set of axioms, and probability is just anything that satisfies this set of axioms. And you know, those very simple, very intuitive, I would say, axioms saying probability is a positive number, non-negative number. They add up to 1 if you count them properly. And the third axiom, which is crucial for our consideration here, is that probabilities of exclusive events add up. You have to just add up probabilities. Except that, you know, nature doesn't know anything about Kolmogorov and Kolmogorov axioms and ignores them. So the third axiom is completely ignored by nature. And if you run an experiment, and there's this famous double slit experiment, where when you run it, the probabilities simply do not add up. What you see is something different. And to account for that something different, you have to change probability to probability amplitudes and add them. And so that more, and there's more to it. And then the whole thing that you see, that the reason we start using probabilities has even sort of a deeper layer to it. The question is that it seems that the quantum randomness that we see in quantum experiments is inherently different. I don't know how much more time I have, so I just have to, do I still have 15 minutes? Okay, thanks. So you see that the thing is, if you take a very simple experiment, like you send a single photon on a beam splitter, I say a simple experiment from the, you know, like Gedanken experiment, right? So to take a single photon, tell this to an experiment, to a quantum optician, and they will get nervous. But if you consider an experiment where you have a single particle, say a photon, going on a beam splitter, and then you put 2 photodetectors, one in the reflected beam and one in the transmitted beam. And then you repeat this experiment many times. And even though, if you assume that the preparation is exactly the same, so the initial condition before you start the experiment, before you release this photon, the photon will be exactly the same frequency, the same everything. Nonetheless, sometimes it's reflected and sometimes it's transmitted. And that is very unusual, because the nature, you know, deterministic worldview tells you, okay, if you prepare something exactly in the same way, the nature should just evolve it in the same way. And some people were very unhappy about it. And if you feel uncomfortable about this, you're in good company, because Albert Einstein was one of them who said, maybe it's not identical preparation. Maybe apart, you know, from the quantum mechanics point of view, it is identical. But maybe the quantum physics or quantum description is not the end of the story. Maybe there's a deeper layer, something that, you know, we call hidden variables. Maybe those preparations are not exactly the same. In each case, there may be some other variable that is different, and therefore it determines whether the photon is reflected or transmitted. And Einstein actually worried a lot about those foundational aspects, about the randomness, about the locality. So he certainly would like to have a theory where there's no instantaneous communication from two spatially separated regions, so that it's not that immediately what I do here is transmitted to some other part of the universe. And he also was very uncomfortable with the statistical aspects of it, so the fact that you cannot make a precise predictions. And he came up with various ingenious thought experiments where he showed that there's something not quite right. And he truly believed that sooner or later we'll find a better description. So he was okay with the provisional character of quantum physics. He didn't say it was wrong. He said it's correct, but it's not complete. So that means that there will be probably a deeper description of that. And probably the most famous paper, it was in 1935, with two of his colleagues, Podolsky and Rosen, kind of expressed this view that quantum physics is okay-ish for the time being, but that's not the end of the story. There's probably something deeper, something more profound, something that will remove the notion of randomness, or will revise the notion of how different objects communicate with each other. He actually probably much more cared about locality than randomness, but that's another story. And here comes, sometimes later, about 30 years later, comes John Bell, who says, those Einstein considerations can be translated into something that is testable in experiment. In fact, his worldview, which we today call the local hidden variable approach to reality, can be tested and can be, in fact, refuted. So it's a refutable proposition. And that was known under the label of the Bell inequalities. I will not go and derive. There's a very simple derivation of those inequalities. You just simply say, if there is such a thing like a local hidden variables, meaning essentially that things are there that determine the values of outcomes are predetermined and there are no instantaneous communication, then there are certain inequalities that have to be satisfied. And then came a series of experiments, one by John Clauser in 1972 when he was a postdoc, and he was told not to work on this kind of experiments because it was considered to be a purely philosophical part, which hardcore, serious physicists wouldn't even touch this kind of thing. Then there was another one, Alain Aspect, who, again, curiosity-driven research showing that the Bell inequalities are violated, refuting Einstein worldview in a sense that there is no local hidden variable. Either you assume that there's inherent randomness or that there's instantaneous communication. You cannot certainly, you can either sacrifice locality or sacrifice determinism, but you cannot have both. So then, what does it, now let's bring together those two lines of thinking. So it turns out that the very consideration that the randomness is inherently there had actually quite an impact on processing of information, on secure communication. And so that led to the concept of the quantum key distribution that, it has a history. I mean, I'm presenting you one approach to quantum crypto, which was my contribution to the field. But of course, there were other thinking. It was the late Stephen Wiesner, who had sort of like the inkling of this idea, mostly based on the uncertainty principle. And Charlie Bennett and Gilles Brassard developed this using the Heisenberg uncertainty. But this connection between the foundations and the quantum key distribution is a sort of independent and probably more powerful and more profound. Not because I contributed it, but in objective terms, I think it's easy to see that it has more impact on letting you drop many assumptions about secure key distribution. And my own sort of inspiration came from reading this 1935 paper by Albert Einstein, where he tries to define this element of physical reality, this hidden variable, saying that if without any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. Now, if you have a background in crypto, you read this and read it again, and you don't think necessarily in philosophical terms, right? You see that essentially this is a definition of good eavesdropping. That's exactly what an eavesdropper would like to do, is to learn the value of the physical quantity, such like a bit value, something that is used to encode information, without disturbing it. So this, now you connect the dots, right? You say, okay, but we know that John Bell showed that there are cases where it's impossible to attribute those elements of physical reality. Either you assume as instantaneous communication, or you assume that there's no element of this physical reality. And then, this very simple, of course, concept and the idea gives you sort of some kind of idea how to proceed. Just take a quintessential Bell scenario where you have entangled photons, and you can show that in this case, you may argue that photons do not carry predetermined values of polarization. So if they don't exist prior to measurements, they are not available to anyone, including eavesdroppers. So then you can use the violation of Bell inequalities for testing for eavesdropping. So that was the basic idea. At the time, I talked to two colleagues of mine who used to work for what used to be called Defense Research Agency in Malvern. It was Paul Tapster and John Rarity. Paul Tapster is a brilliant quantum optician, experimentalist, and John as well. But Paul is one of those who really lives in the lab. It was, I have to say that it was not entirely easy to set up this collaboration, because for some reason, historical reason, in the UK, crypto is funded by Foreign Office, and John and Paul worked in DRA that was under the Ministry of Defense. And somehow they were not supposed to be doing any crypto. And there's lots of red tape around, and at some point, the management was finally persuaded that it is actually okay for them to do this kind of experiments. But it shows that the bureaucracy is pretty much the same all over the place. So we did those experiments showing that Bell inequalities can be used to test for eavesdropping. It was not, I presented it in a very simplistic way, but there was a need for some mathematical gymnastics. Remember, I showed you this figure of merit that you have to estimate how much an eavesdropper can know. So the idea was, look at the Bell inequalities, look at the degree of the violation of the Bell inequality, and infer from that how much information could have leaked to a potential eavesdropper. So that required a bit of a mathematical gymnastics, but essentially it was done. Another interesting thing was, and that was something that I didn't realize when I was working on this, and some other colleagues did later on, was that maximal violation of Bell inequalities is rigid. So that means that if you see the maximal violation of Bell inequalities, there's up to local isometries, mathematically speaking, there's no other way of violating those Bell inequalities but just having entangled photons and performing the measurements that are essentially isomorphic to the violation of the Bell inequality. And that opened an interesting sort of reverse argument, which essentially goes like this, that something that we call today device-independent crypto. Take devices that you don't trust. You buy them from your enemy. You don't have technological capabilities to develop certain things. But you know that a person or agency or another entity that you don't entirely trust, but nonetheless, they can do it and they are willing to sell it to you. And of course, in the usual world, crypto world of paranoia, you wouldn't actually dare to do such a thing because there could be all kind of hidden traps, Trojan horses and the like. But in this particular case, the whole thing is self-testing. So that means that actually, if you get those devices and you see the violation of Bell inequalities, by the rigidity of the Bell theorem, you know that those devices do their job properly. That there's no way for achieving this violation of Bell inequalities in any other way but having genuinely entangled particles there and performing at certain types of the measurements. So you can, so that actually gives you a guarantee that you can purchase devices from the enemy even and use them in such a way that with a confidence that you actually achieve secure communication, which is very nice. Of course, usually we think about the scenario that the agencies, even if we are approaching the device-independent scenario, the agencies are paranoid enough, they wouldn't like anyone else to produce them, but actually that also protects you by errors that you may introduce yourself, either by lack of knowledge or some kind of negligence in the production process. So it's actually a very good of a self-testing and self-certifying that devices do what they are supposed to be doing. But to prove the security of the device independence, it was much more difficult. And in fact, probably the final touch was given by those three people, Renato Renne, who at the time supervised Rotem Arnon Friedman, who was his student at ETH, and together with Thomas Vidik, they came up with the final proof for the device-independent crypto, which essentially boils down to the scenario I proposed. But this is a good example that sometimes your ideas are more clever than you are, right? Then you come up with the idea and don't see entirely the impact of this idea. So that was certainly the case. I don't know which was actually I was looking, I have a pretty good overview of my slide and was not looking at the screen, so I don't know which was the last slide you saw, but essentially that I was telling you about Renato Renne and Rotem and Thomas Vidik, who proved the security of the device-independent crypto. And this is in a way for real because in about 2 years ago, there were the first sort of a series of experiments demonstrating the device-independent crypto. And that came from 3 groups here. The one was the Oxford group of David Lucas, another was Harald Weinfutter group from Munich, and the Chinese group of Jianwei Pan. This actually brought Bell theorem, the curiosity-driven research, to the point where you can see an interesting sort of a symbiotic coexistence of the two. It's certainly the crypto gave credibility to, well, if the credibility was needed to this curiosity-driven research. So those people who work on the foundations of quantum physics were not perceived anymore as a bit on the outskirts of sort of outliers, right? And on the other hand, quantum and quantum tools developed by quantum physicists actually contributed to the repertoire of tools that cryptographers can use, giving the most secure system for secure communication that we have today. So there is certainly, and moreover, it was all these crypto applications that were absolutely, they were actually pointing at the very important aspect of it, that the Bell inequalities have to be violated with all the loopholes closed. And that really happened in a sequence of experiments later on. So it was already clear that Bell inequalities is not just only the philosophical thing, it is also a tool for secure communication, and therefore various, there was a need to do a little bit more experimental work. And in 2022, some of our colleagues who worked on implementing the violation of Bell inequalities, from John Clauser to Alain Aspect, to Anton Zeilinger. Clauser and Aspect were basically, their work was curiosity-driven. Anton already had advantage because he knew that quantum key distribution of that kind may rely on the violation of the Bell inequalities. So see, he certainly saw the value of closing all the loopholes in this thing. And this may be end of the story, but it isn't quite. There are many questions you can ask about this, the Bell inequalities. What about the situation where there's still a possibility that we live in a super-deterministic world? Bell inequalities requires a certain degree of either randomness or free will in choosing the setup of those devices. Where is this coming from? What if it is predetermined? And another interesting story is to putting it in the context of many world interpretations, to which I personally subscribe to, where you don't just basically assume that there's just like one outcome for the experiment. So rephrasing the whole thing is possible, but I didn't present this kind of narrative. But then what I'm saying here is that there are a few questions that remain, maybe more than just a few. So it's still an open question and a subject of interesting research, not only on the experimental side, to have it implemented, because that would be actually truly fantastic to have a self-testing devices that you can use for secure communication. But it is equally interesting from the fundamental point of view to understand the notion of randomness better. Can you amplify randomness? Can you have more randomness that you put in? Is this the randomness in the Democritus sense, or is it in the is it sort of subjective, or is it objective? Is it more epistemic, or is it more ontic? So there's a place for philosophers, computer scientists, mathematicians, logicians, and cryptologists to play. So therefore, I thought I'll give you a glimpse of this field because it's fun, it's fascinating, it's important, eventually probably also even practical. So thank you very much for your attention.